Hi everyone, in this video we are going to revisit the problem of finding the minimum speed a particle needs to have to make it all of the way around an elliptical loop-the-loop, and the loop has a horizontal major axis, its semi-major axis is A and its eccentricity is E. So this time we're going to take the approach of using constrained Lagrangian mechanics. Now I'll just start with a bit of a warning that this is not intended to be the best way or easiest or most direct way to solve the problem. I've already done another video solving this using what I would call the easy way, where we consider the particle to be moving instantaneously in a circle and think about radius of curvature and consider the forces. However, I thought it was a fun example of doing Lagrangian mechanics in a non-standard coordinate system, and if you're willing to make it all the way through the maths involved, then I hope you'll agree that by the time we get to the end, it's pretty satisfying to derive the same conclusion we got last time, but using this more formal method. This method does also have some other advantages. For example, it would allow you to calculate the position along the ellipse where your particle would lose contact if it's not going fast enough to make it all of the way around. So we do get a little bit more information than we did in the previous video. So for those of you who have not been put off by that warning, let's get into solving the problem. And I'm going to start by writing down the Lagrangian in Cartesian coordinates in order to explain why we should really be using a different choice of coordinate system. So if we were to use Cartesian coordinates, if we just put down a standard set of x and y axes at the center of the ellipse, then our kinetic energy in our Lagrangian would be a half m times x dot squared plus y dot squared, where a dot is a time derivative, and then your potential energy would just be mg times the height. The height would be y up to a constant, and so we subtract off mgy in our Lagrangian. Now, the way you deal with constraints in Lagrangian mechanics is by setting up a function of the coordinates, which is always supposed to be equal to 0. I have a whole video going through the general method for that if you're not familiar with that. But here our constraint function, let's call it g of x and y, would basically be something that comes straight from the Cartesian equation of an ellipse. So we would have to make sure that x squared over a squared, where a is the semi-major axis, plus y squared over b squared, where b is, let me just mark this on the diagram, b would be your semi-minor axis, sort of half vertical height of the ellipse. So that stuff minus 1 is supposed to be equal to 0, because the equation of ellipse is x squared over a squared plus y squared over b squared equals 1. Now, although your Lagrangian looks pretty simple here, your constraint function involves both x's and y's, and they're also both squared, and that is going to lead to some complicated algebra when you try to solve or try to set up your equations of motion. Your x's and y's will all be coupled together because they both appear in the constraint function. I did try to work through this problem in Cartesian coordinates, and I was not able to solve the resulting system of equations. If anyone's feeling particularly enthusiastic, maybe you can have a go at working through this problem in Cartesian coordinates. I'd be very interested to hear about it if you can solve it. But this is my justification for introducing a different coordinate system. So the coordinate system which is appropriate for this problem is the elliptic coordinate system, because the coordinate curves, or the coordinate curves for one of the coordinates, are ellipses, as the name implies. And because our particle is moving, was constrained to move along the surface of an ellipse, then our particle will basically be moving along one of the coordinate curves if we were to choose our coordinate system correctly. Now, I'm not going to be introducing elliptic coordinates from the beginning here because I've already done a fairly long video on that, so have a look at that if you're not familiar with elliptic coordinates. But let's write down how the elliptic coordinates are related to x and y and use that to write down our Lagrangian in our new coordinate system. I've just written down there the definitions of, or the implicit definitions of your elliptic coordinates mu and nu in terms of x and y. You'll notice there's this parameter c that appears in your coordinate definition. C is not one of the coordinates. It's a constant that basically determines where the focus of the ellipse is. But we're just going to leave it as c for now. We'll think towards the end about how that's related to the semi-major axis. Now, the reason why this is a good coordinate system to use is, well, think about what your new constraint function would be. If we call our new constraint function f, then f of mu and nu would be mu minus some constant. We don't really care what that constant is at this stage, is supposed to be 0. Basically, we're saying that the mu coordinate is supposed to be 0, and I've already shown in my video on elliptic coordinates that curves of constant mu are ellipses. And so you get this very simple constraint function which only depends on mu, and that is going to drastically simplify the algebra that we've got to do. So that's your constraint function. How about the Lagrangian itself? Well, to write down the Lagrangian in terms of mu and nu, you are going to need to know x dot and y dot in terms of mu dot and nu dot. So we can get those by just differentiating our coordinate definitions. If we do that, then x dot is going to be, we've got to use the product rule and also the chain rule because x depends on both mu and nu. So if we differentiate with respect to mu first, or differentiate the cosh mu term first, you get a mu dot from the chain rule, you get c, you get sine mu by differentiating the cosh, and your cos nu stays as it is. Then your second term from the product rule, this time you're going to get a nu dot, you're going to get c, your cosh mu stays as it is, but then you differentiate the cos nu and you get minus sine nu. Then we do a very similar thing for the y definition. Y dot is going to be mu dot c. This time your sine becomes a cosh, so cosh mu sine nu, and then we differentiate the sine nu part. This time we get a plus, it's plus nu dot c. Sine mu stays as it is, but then this sine just turns into a cos. So there's x dot and y dot in terms of the derivatives of your elliptic coordinates. So that helps you to write down your kinetic energy term in terms of mu dot and nu dot. Let's write that out explicitly. Kinetic energy EK is going to be, well, you're always going to have your half m. Then you've got the x dot squared plus y dot squared. So you have to look at these expressions and imagine squaring those and adding them together. There is a common factor of c in every single term there. So when we square them, we're going to be able to take out a common factor of c squared. And then let's start by thinking about the mu dot terms. So let's put a mu dot squared here. Right, everything's squared, so there's not going to be a mu dot term, but there will be a mu dot squared term. From the x dot equation, you are going to get sine squared mu and cos squared nu, right, by squaring that. And from the y dot equation, you're going to get plus cosh squared mu and then sine squared nu. The reason I've written it like this is because, well, think about what happens with the nu dot components. You would get cosh squared mu sine squared nu from the first line, and then sine squared mu cos squared nu from the second line. Those would be added together, and that's the same bracketed term that we had for the mu dot squared terms. So I can just put here plus nu dot squared because the nu dot squared term has that same sort of prefactor in terms of mu and nu. What about the cross terms in terms, well, the terms that are proportional to mu dot nu dot? Well, because these have opposite signs, they would cancel each other out, right? Your mu dot nu dot terms are going to be, you'll get sine mu cos nu times cosh mu sine nu from the x dot squared part, and that will be negative, and then also be a factor of 2 there. But then you'll have exactly the same stuff multiplied together from the y dot squared. You'll get cosh mu sine nu sine mu cos nu. That's all of the same stuff, just in a different order. So you get the same terms but with opposite signs, and so they cancel, and that's our full expression for the kinetic energy. So at this point we can write down our full Lagrangian in terms of the elliptic coordinates. L is going to be, well, we've got, I can actually just copy and paste that whole thing. I'm going to just reorder the terms because I think it looks a little bit nicer that way. Put my mu dot squared and nu dot squared at the end like that. So that's our kinetic energy part. And then we have to subtract off the GPE, which is minus mgy. But that's easy to deal with because we know that y is c sine mu sine nu. So I just put down here minus mgc times sine mu times sine nu. So there is our full Lagrangian in elliptic coordinates. So now that we've got our Lagrangian, we'd better start differentiating it with respect to the coordinates and their time derivatives so that we can write down our equations of motion. So let's do the mu equation of motion first. We're going to need dl by d mu. So let's differentiate that. We still get our half mc squared prefactor. If we do this term by term, you've got to differentiate sine squared. You can do that with the chain rule. So you get 2 sine mu and then cos mu from the chain rule. You've still got your cos squared mu. Okay. Then you have to differentiate the cos squared. Again, you do it the same way. You get 2 cos mu, sine mu using the chain rule, and then sine squared nu. Then you still have these squared derivatives at the end, mu dot squared plus nu dot squared, because they don't depend explicitly on the coordinates themselves. Then you just have to differentiate this sine mu part of your potential energy bit, and you get minus mgc times cos mu and then sine nu. Now we can use a useful trig identity here. Notice that you've got 2 sine mu cos mu and then the same thing but flipped around, added to each other with factors of cos squared and sine squared. Now notice that cos squared of anything plus sine squared of anything is equal to 1. And so overall this big bracketed term is just 2 sine mu cos mu. The 2 then cancels with that prefactor of a half, and this whole thing simplifies quite nicely to mc squared sine mu cos mu times your squared derivative bit mu dot squared plus nu dot squared, and then minus the mgc cos mu sine nu. So you've also got to differentiate the Lagrangian with respect to the time derivative of mu dot. I think that's a little bit easier because I can basically just start by copying and pasting that whole prefactor, because the only bit that depends on mu dot is this mu dot squared here. If I differentiate that, I just get 2 mu dot. So that 2 will cancel with the half there. So I get rid of that factor of a half, and then I just put mu dot there, and I can move the whole thing over like that. So there is our dl by d mu dot. So here's our equation of motion. This lambda here, or more precisely, this lambda df by d mu term, where f is the constraint function, that physically represents the constraining force. So that's going to be very important later on. If we just plug in all of the results that we've got so far into that general equation of motion, let's see what happens. So your dl by d mu bit, just, well, it's that bit that I've just copied there. Then I have to subtract off the time derivative of dl by d mu dot. dl by d mu dot was this whole thing here, so I just put that there. Close the brackets on my time derivative. I add on lambda df by d mu, where lambda is my Lagrange multiplier. df by d mu, well, look all the way at the top. And remember that f is just mu minus a constant, so if you differentiate that with respect to mu, you just get 1, which makes this very easy. It's just plus lambda at the end, and all of that stuff is supposed to be 0. At this stage, we can get a very nice simplification by applying our constraint function. Note in particular that if mu is a constant, mu minus something is 0, by differentiating that, you get the fact that mu dot is identically 0. And so this term here, which is proportional to, well, you're differentiating something which is proportional to mu dot, that entire d by dt bit just disappears. And so again, I can do this more quickly by just copying and pasting. I can take all of that stuff from that line. The d by dt bit just vanishes, and then I get plus lambda is equal to 0. So this is our first equation of motion. Maybe at this stage I can actually do a bit of simplification. I can divide through by m, so get rid of that m, get rid of that m. Then I'm going to have lambda over m instead of just lambda at the end there. You can also divide everything by c, so that c squared becomes a c. This c here disappears, so you just have a prefactor of g there, and then your Lagrange multiplier bit is now really lambda over mc. So let's call that equation 1. That's going to be very important later on. Or in fact, what I think would be even nicer to do would be to divide everything by cos mu at this stage. So that cos mu disappears, that cosh mu disappears as well. Let's just group these terms nice and clearly together. So the cosh mu's have disappeared from the first two terms. Then I've also got to divide my lambda bit by cosh mu at the end. Let me just write that out in full. We've got then plus lambda over, that was mc times cosh mu is equal to 0. I think that's going to make things a little bit easier later on. Okay, so let's go back to our Lagrangian, which is that second line there, and now we start differentiating with respect to nu to get our other equation of motion. So dl by d nu, we can use almost an identical method, but we're going to be using hyperbolic identities instead of ordinary trig identities this time. So we've still got our half mc squared. Differentiate the first bit with respect to nu. You're going to get, well, your sine squared mu will stay as it is. You're going to get, from differentiating cos squared of nu, you will get 2 cos nu times minus sine of nu from the chain rule. So I put my minus 2 there, and then I put cos nu sine nu. Similarly, then I've got to differentiate the second bit, the sine squared nu. I'm going to get plus 2 cos squared mu sine nu cos nu from the chain rule, and then we get our mu dot squared plus nu dot squared. Then I have to differentiate the potential energy part with respect to nu. All that happens there is your sine changes into a cos. So we've got minus mgc sine of mu times cos nu. Right, so now notice that you've got 2 cos nu sine nu, 2 sine nu cos nu. And the stuff by which those terms are multiplied is you've got cos squared mu in the right hand bit, and you've got minus sine squared of mu on the left hand bit. We use the hyperbolic trig identity that cos squared minus sine squared is 1. And so we combine the terms into in the brackets into a single term, and that prefactor of 2 cancels with the half in the beginning. And then that all simplifies nicely down to mc squared times sine nu cos nu times mu dot squared plus nu dot squared minus mgc sine mu cos nu, like so. Again, differentiating with respect to the time derivative, nu dot is a little bit easier because nu dot only appears in that circled bit there. I differentiate that, I get 2 nu dot, the 2 cancels with the prefactor, and so I can do some copying and pasting, take that whole bit, put that down there. I've forgotten my equals sign, so let me add that in. That equals that multiplied by nu dot, and there's our dl by d nu dot term. Let's use all that to form our second equation of motion using the nu derivatives. We'll start with the dl by d nu, so I just copy all of that stuff and put it there. Then we're going to subtract the time derivative of dl by d nu dot, as the Euler-Lagrange equations tell us to do. So we are going to get, let's just write it as a time derivative for now, so minus d by dt of all of this, right, that's dl by d nu dot. Then I close my brackets. I've got a plus lambda times df by d nu, but because f only depends on mu, we don't get a lambda term there. Right, df by d nu is 0. That's why this is a nice coordinate system to use for this problem, because the lambda only appears in one of your equations of motion. So I can just set that equal to 0. Let's also tidy up some of the constants. We can divide through by mc so that that first bit just becomes c. The second constant just becomes g. And again, down here, we get a c. Right, so let's use the product rule to expand our time derivative. I'm just going to copy out that first line again, so that stuff is going to stay unchanged for the time being. So let's apply the product rule. We've got 2 things multiplied together. We've got this big bracketed term with hyperbolic functions and trig functions, and then we've just got that multiplied by nu dot. So let's do the easy bit first and just differentiate nu dot with respect to time. That just adds another dot and gives you nu double dot. So I'm going to have to subtract. I can do some copying and pasting again. Right, we're leaving this whole bracketed bit unchanged. So I copy that. there. I don't need my underline. But then our new gets a second dot, so new double dot. I think I'm going to need some more space, so let me move that over to the left a little bit more. So now we're going to have to differentiate with respect to time, that underlined bit, the bracketed term. And to help with that, firstly, remember that mu is a constant. That's according to our constraint function. So remember that only nu is varying with time. So if we look at that first bit first, we differentiate that with respect to time. The sine squared mu will stay as it is because it's a constant. Then you will get minus 2 cos nu sine nu times nu dot from the chain rule. Right. I'm not writing this down because we've already done some similar stuff earlier, so I'm trying to go a little bit more quickly. So overall, from that first bit, you've got minus 2 sine squared mu cos nu sine nu times nu dot. From the second bit, your cos squared mu, again, it's constant, that doesn't change. If you differentiate the sine squared, you're going to overall get 2 cos squared mu sine nu cos nu times nu dot. Most of the stuff in those two terms is the same. As we did earlier, we apply the trig identity, cos squared minus sine squared is equal to 1. And after going through all of that, you conclude that you get minus 2c sine nu cos nu times nu dot squared is equal to 0. This is now squared because you got an extra factor of nu dot from each of these terms from the chain rule when we differentiated those. So we can tidy some things up here. Firstly, remember that mu is a constant, so we can actually get rid of this mu dot squared bit here. So let's erase that and just leave the nu dot squared. Then notice that this term and the final term have the same form. So you've got one of them, and then you've got minus 2 of them at the end. So overall, that combines to give just minus c sine nu cos nu dot squared. So if you collect those together, then you'll find that all of the terms have a minus sign in front of them. So you can flip the sign of all of the terms and make them all positive. And so overall, what you'll get by doing that is c sine nu cos nu dot squared. Let's put the nu double dot term next. So we get plus c. In fact, I can copy and paste all of that stuff. Let's put that there. And then at the end, maybe I should move this across so that I can fit this all on one line. That didn't go very well. Let me try again. Okay. We've just got to add on this bit as well. Remember, we flip the sign of everything. So we've got plus g sine mu cos nu is equal to 0. Now at this point, I'm going to use a useful trick involving the chain rule, where you write your acceleration term, second derivative term, nu double dot. You can write that as d by d nu of a half nu dot squared. Now that's a pretty standard trick in mechanics. I think I did a quick derivation of this in my video about particles sliding down a sphere using Lagrangian mechanics. So either have a look at that, or if you want me to do a full video explaining how that works, I can do that. But for now, let's just take that as a given. It's a useful identity. And the next part of this, we have to basically use the product rule backwards. We have to basically spot that the first two terms of our equation of motion could have come from the product rule. So let me start setting that up. We're going to write the first two terms as d by d nu of something. Now, one of those things is going to be half nu dot squared, because we've just said that this nu double dot term is the same as d by d nu of a half nu dot squared. So we can start by putting a half nu dot squared. Let's also include the c prefactor, which is common to both of those terms. Now, to figure out what the second thing is, remember, this has come up, I think, twice so far in this video, so I won't explain why again, but the derivative of that bracketed term is 2 sine nu cos nu. That comes from using a hyperbolic identity. So I can take all of that bracketed stuff there, copy and paste that here, and then, oh, my mu's gone missing. If we were to differentiate all of the stuff in the square brackets using the product rule, we would recover the first two terms of the previous line. So then all we have to do is put our plus g sine mu cos nu is equal to 0 at the end. The reason why this is useful is we can now very straightforwardly integrate this whole thing with respect to nu, because if we do that, integrating the first term basically just makes the d by d nu disappear. So integration is the opposite of differentiation. So we do that integration, we just get the stuff that we would have differentiated. Then remember, mu is a constant, and cos nu integrates to sine nu. So we just get plus g sine mu sine nu. It's no longer equal to 0, it's equal to the integral of 0, which is just some constant. Let's call that constant k. So to find the value of k, we can apply some initial conditions. Here is where this initial speed of u at the bottom becomes relevant. Well, you can either refer to Wikipedia's article about elliptic coordinates, or you can look back at my video on elliptic coordinates. Either way, hopefully you'll be able to convince yourself that the new value, if you're directly below the center of the ellipse, the new value on that ellipse is 3 pi over 2. So our particle starts with a new value of 3 pi over 2. Basically, your new starts at 0 over here, and as you go around anti-clockwise, increases from 0 to 2 pi, kind of like just the ordinary angle that we might define in polar coordinates, but a little bit more complicated. So our initial condition then is just that when nu is equal to 3 pi over 2, we know that x dot is equal to u. So when u is 3 pi over 2, x dot is equal to u. What about in terms of elliptic coordinates? Well, this is one of the things that we got at the very beginning of the video when we were finding kinetic energy for our Lagrangian. So I've just quoted that result there. All of that stuff is supposed to be equal to u. If we plug in nu is 3 pi over 2, then, well, cos of 3 pi over 2 is 0. Sine of 3 pi over 2 is minus 1. And so we conclude that nu dot is equal to u over c cos mu. Mu dot is always 0, remember, because mu is a constant. But nu dot is equal to this when nu is 3 pi over 2 at the beginning. So let's substitute that into our previous line to find an expression for k. So you're going to get half c times all of that stuff squared. So half c times u squared over c squared cos squared of mu. What about this bracketed bit here? Well, again, remember that cos of 3 pi over 2 is 0, so that bit would disappear. Sine of 3 pi over 2 is minus 1, so when you square it, you get 1. And so the bracketed bit there just reduces to cos squared of mu, quite conveniently. Then the second bit is going to become minus g sine of mu. That's equal to k. Then you get some simplifications. The cos's cancel, one of the c's cancels, and so you conclude that k is equal to u squared over 2c minus g sine of mu. So what can we do with that? Well, we just plug it back into our integrated equation of motion up here. Let's copy that. Let's take that, get rid of these things, and we just replace our k by u squared over 2c minus g sine of mu. Okay, so we're getting there. Let's just clean up this equation a little bit. It's times by 2 to remove the fraction at the beginning and move some of the terms around. So, all right, we're going to have this c nu dot squared term and all of this bracketed stuff. Let's move the g sine mu sine nu to the other side so that we can combine it with the minus g sine mu on the other side. So we are going to get that is equal to u squared over, we've got rid of the 2 now, so it's just u squared over c. Then we are going to get minus 2g sine mu, 2 because we multiplied by 2. We are factoring out the sine mu, and so we're going to get 1 plus sine of nu. We could call that equation 2 if you wanted, because that's ultimately come from our second equation of motion in terms of nu. So we're now in a position where we can almost combine together equations 1 and 2. One more simplification we should make first is remember that this mu dot term is already 0. So we get rid of that. And so you've got your first term is already c nu dot squared sine mu. let me just write that in that way. So c nu dot squared sine mu, and you just move that over here. So what you can then do is note that you have c nu dot squared here as well. So you can use equation 2, rearrange equation 2 to get c nu dot squared in terms of the coordinates themselves, and substitute that into equation 1. So if we do that, our expression for c nu dot squared is going to be a big fraction with the right hand side of equation 2 on the top. We are going to have to divide all of that by the stuff that c nu dot squared was multiplied by in equation 2. So we divide by all of this. We have to remember to multiply by sine of mu when we put that into equation 1. So we get sine mu there. Then we've got our minus g sine nu. At this point, we may as well set lambda equal to 0, because ultimately this problem is all about finding out whether the particle makes it all the way around the loop, right? Remember, the interpretation of lambda is that it's the constraint force, which in this case really means the normal contact force between the elliptical loop and the particle. So if we're interested in whether the particle ever loses contact or not, we should set lambda equal to 0 and see whether there's any solution for the value of nu at which that contact force becomes 0. So we set lambda equals 0, this stuff all disappears, and then this is just supposed to be 0. I'll just put in brackets as a reminder, that's come from setting lambda equal to 0. So let's get rid of this big fraction by multiplying everything by the denominator. All right, so we're still going to have the numerator in our tidied up version of the equation. Right, u squared over c. Let's multiply out this this sine mu as well. So I need to put a sine mu term next to the u squared over c. All right, so that gets a sine mu. This sine mu here is going to be squared, so sine squared mu, because it's been multiplied by that sine mu over there. Let's also move the g sine nu onto the other side. So I'm going to get g equals g sine of nu, and then we multiplied everything by the denominator. So I have to copy all of this and put that on the right hand side, just about bits on the page. So what we have here is really an equation where the only unknown is nu. Remember, mu is fixed, so we're basically trying to solve this equation for nu, but nu appears both via cos and sine. So we might want to use some trig identities to get everything in terms of either cos or sine. Because you've got a sine here, it would make sense to write your cos squared as 1 minus sine squared. So if we do that on the right hand side, keep our g sine nu at the front there, you're going to get then a sine squared mu. You're going to get a minus sine squared mu sine squared nu, right? This is just from applying cos squared equals 1 minus sine squared. Then you've still got this term, which was originally there, all right, plus cos squared mu sine squared nu. Then you can apply a hyperbolic trig identity. Notice that second two terms are proportional to sine squared nu, and you've got a cos squared minus sine squared, which is equal to 1. And so your entire right hand side simplifies down to g sine nu times sine squared mu plus sine squared of nu. So remember that ultimately what we want to do is get a condition on u, the minimum value of u required for a complete loop. So it might be a good idea to move some of this other stuff to the right hand side of the equation so that we can work towards getting u on its own. If we do that, for the time being, we've got u squared over c times sine mu. Which terms are we going to get on the right hand side? Well, you'll get 2g sine squared mu from that term that we've just moved across. So it's 2g sine squared of mu. You're going to get also 2g sine squared mu sine nu. But there's another one of those terms, same type of term, already on the right hand side. G sine nu sine squared of mu. So you've got 3 of those in total. So I'm going to put here plus 3g sine squared of mu sine nu. And finally, you've got g sine nu times sine squared of nu, which is plus g sine cubed of nu. I am going to do a bit more algebraic manipulation, divide through by g, and also divide through by sine of mu. to get u squared over gc on the left-hand side. The right-hand side, again, if we recombine some of the terms, you get, it's going to be a big fraction now, sine squared of mu times 2 from this 2 here, and then plus 3 sine nu from that second term, so plus 3 sine of nu. Then we've got that plus sine cubed of nu as well. Remember, we divided the g out. Then we've now got a denominator of this sine mu, which we've divided through by. So divided by sine of mu. Now consider how the right-hand side of this equation depends on nu. And in fact, more specifically, consider how it depends on sine nu. So the right-hand side is actually a monotonically increasing function of sine nu. And so the maximum possible u squared that we're going to get, let me write this down, the maximum required value of u squared is going to occur when sine nu has its biggest value. So when sine nu is equal to 1, that corresponds to nu being pi over 2, which corresponds to the top part of the ellipse. Okay, and so this is again telling us something that's ultimately very intuitive. It's saying that the hardest part of the ellipse to reach is the very top part, right? That the top of the ellipse will give you the maximum required initial speed in order to reach that point. So let me just make a note that that is at the top. So the idea is then if your u squared is any bigger than it is when sine nu is equal to 1, then you'll definitely make it all the way around. And so we come up with this condition for a complete loop, which is u squared over gc is bigger than, if we plug in sine nu is 1, 2 plus 3 times 1 is 5. So you get 5 sine squared of mu, and then just plus 1 from this 1 cubed, and then all divided by sine of mu. Also note, by the way, that this previous equation that we had for u squared over gc is actually useful if you want to know in general for a given value of u squared at which point on the ellipse your particle will lose contact, if at all. If you were to solve this for sine of nu and therefore nu, that's what that would tell you. It's like the point on the ellipse at which the particle loses contact. So the final step is just to convert our condition that we've got here into a form that is expressed using the parameters that I originally gave in the question, which were semi-major axis A and eccentricity E, because it's not very useful directly to have it in terms of this this thing mu. So what we can do is use the fact that cosh of mu is 1 over the eccentricity of the ellipse. This is a result that I derived in my video on elliptic coordinates, so I'm not going to prove this here. But because cosh of mu is 1 over E, and cosh squared minus sine squared is 1, that implies that sine of mu is the square root of 1 over E squared minus 1. We can then substitute that into the inequality above. So we get that u squared over gc is bigger than 5 times, well, all of that stuff without the square root because it's been squared, so 1 over E squared minus 1, then plus 1, divided by the square root of 1 over E squared minus 1. Expanding the brackets then gives 5 over E squared. It's going to be minus 4 because you get minus 5 from that bit and then you add 1 at the end. So 5 over E squared minus 4 over root of 1 over E squared minus 1. Then we can multiply the top and bottom by E squared to remove these fractions within fractions. So you're going to get 5 minus 4E squared on the top. On the bottom, you're going to get E times the square root of 1 minus E squared. Right, we've multiplied top and bottom by E squared there. And so if we put U squared on its own on the left-hand side by multiplying through by GC, we get U squared is bigger than 5 minus 4E squared over, I'm going to leave this as just root 1 minus E squared. Remember, we had that extra E on the bottom there. So we're going to get G times C divided by E. Here is where we have to use basically the definition of eccentricity for an ellipse. So the eccentricity is, let me get this the right way around, it's the x-coordinate of the focus C divided by the semi-major axis A. So if eccentricity is defined as C divided by A, then c divided by e is just the semi-major axis A, and so we can replace that c over e by A, which is exactly the same result that we derived when we just used the radius of curvature of the ellipse and considered it to be moving instantaneously in a circle. So there's our result. We've got our minimum speed required. I think that's a good place to stop this video. I certainly need a bit of a rest after all that maths. I've gone through all the intuition and interpretation of the equation, or the formula that we've got in my other video on this topic. And if you've made it all the way through, then thank you very much for watching, and I hope to see you again soon.